Okay, so 1.3 even and odd functions. First off, we're going to look at even functions so you can tell what they actually are. So what does it mean to be an even function? It all depends on how it's symmetric. So when you're looking at your graph, how is it symmetric? What is it symmetric about? So the even functions are always going to be symmetric about the y-axis. So what that means is if I were to look at the y-axis here, fold it in half, then it's going to be perfectly on top of itself. If you fold it in half on the y-axis, it lays perfectly on top of itself. That's what symmetric about the y means. If we were to look at it as a point, then that could also mean for every x, y, so for every parentheses x comma y, so that just means for every point, every positive point, there exists negative x comma y. So that just means for every positive point that we would find in quadrant 1, there exists a point in quadrant 2 where the x sign got flipped. And that gives you that fold over from quadrant 1 to quadrant 2. One of the things you're going to have to do is determine algebraically if a function is even or not. So here are the steps for determining if it's even. First step, you're going to plug negative x in for x in the original. So first step, plug negative x in for x in the original. Second step, if it simplifies to equal exactly the original, then it's even. So first we're going to plug negative x in, we're going to simplify it, and if the plugged in version is the exact equal of the original version, it's even. So let's try it and see if this one's going to work. So we're going to plug in negative x every place we see x. So that would look like y equals negative 3. I always put parentheses every place I'm going to plug in. So parentheses negative x, squared is going to go outside of your parentheses, plus 4. And then we simplify it. So think about what happens when you square a negative. A negative times negative, that's squaring, becomes a positive. So this is technically, right here, a positive x squared, after we simplify it, times negative 3, which then would become negative 3 positive x squared, plus 4. So this was our simplified, and this was our original right here. So we compare those two. Did this one match exactly this one? Yes, they did. So then it's even. Okay, so that's how you find even functions. Graphically, are they symmetric about the y? Algebraically, when I plug negative x in, it gives me the exact same thing as the original. The notation for this, you might also see, is if I do f of negative x, so that's just saying I plug negative x in, if it's equal to the original f of x. So plugging negative x into it equals the original f of x. Therefore, it's even. So these little 3 dots right here, those mean therefore. So if f of negative x is equal to f of x, therefore it's even. So that's another way you could see it written. Okay, odd functions. How are these different than even functions? So odd functions, their meaning is they are symmetric through the origin. So your origin is always 0, 0. So what that means is that it's symmetric from this quadrant through to the other quadrant. So you can kind of think of those two as like not only they're not reflecting over the diagonal, but they're more like rotating. If you took quadrant 1 and you rotated it into quadrant 3, would it be on top of it? And it is. So that's how you can tell through the origin symmetry. So this means for every positive x, y, so for every point that's in quadrant 1, there exists a negative x, negative y point. So negative, negative is quadrant 3. So for every quadrant 1 point, there's a quadrant 3 point that matches it. And that could be true for like quadrant 2. For every quadrant 2 point, there's a quadrant 4 point. Those could still be symmetric through the origin. Algebraically, how do we determine if it's odd? So we can find it graphically, algebraically. Here's your steps. First step, same as the other one, same as even. Plug in negative x for x in the original. Second step, if it simplifies to the exact opposite, it's even. Odd, sorry, we already did even. It's odd. So exact opposite means that all signs have been flipped. So if it was positive in the original, when we simplified, it's now negative. So if everything is completely flipped, exactly the opposite, then it's odd. So let's test it out. 2x cubed minus 4x. So we're going to first plug in negative x every place we see x. Y equals 2. Plug in negative x. Minus 4, plug in negative x. So every time I plug in, I put it in parentheses. So a negative cubed, that's a negative raised to an odd power, is going to end up being a negative, right? Negative times negative is positive, times another negative is negative. So this whole thing, because we're going to get negative x cubed times 2, will end up being negative 2x cubed. Did I lose anybody on that? You good? Okay. Negative 2x cubed here. Negative 4 times negative x would give me a positive 4x. So this is the simplified that we need to check with the original. So simplified original, 2x cubed, negative 2x cubed. Minus 4x, positive 4x. So everything is completely opposite. That then means this would be what? Odd. So in function notation, the way we would write this is if plugging in negative x, so f of negative x, is equal to the exact opposite of f of x, so we would write that as minus f of x, then, or therefore, it's odd. So if plugging in negative x to the original results in an equals of f of x being completely opposite, or minus f of x, it's odd. So then how can we determine if it's neither odd nor even? So pretty much the same way. If we plug in negative x for x in the original, and it does not or doesn't equal f of x or negative f of x, then it's neither. So this means that it doesn't equal the original. So we plug in negative x, and it doesn't equal the original, and it doesn't equal opposite of the original, then it's neither or neither. Graphically, if it's not symmetric about the y-axis, it's definitely not even. If it's not symmetric about the origin, it's definitely not odd. So if it's neither one of those, then it's neither. So those are the two main ways, graphically and algebraically. There's a third way, and it's kind of a little nifty trick to know. So how can we use exponents? Exponents can help us determine if it's even, odd, or neither. So if you were asked to algebraically prove it, you can also use this just to verify that you did it right. So even though you have to show it algebraically, you can use it just to help you. So let's do the first one, and I'm going to show you how exponents could have helped us. So the first one was negative 3x squared plus 4. Y equals on that. So if we look at just the exponents only on all of the terms, our first exponent here, 2, is even. Our next exponent, or our next term, is 4. There's technically not an exponent there because there's no x. So if there's no x and it's just a constant, you can technically write that as x to the 0, because anything x to the 0 is actually 1. So 4 times 1 is 4. So x to the 0 represents like a constant where you wouldn't have an exponent. And this exponent is actually 0, which is even. So we consider 0 even. So if all exponents, write this down, if all exponents are even, the function is even. Pretty cool trick. Same thing happens with odd. So if we look at our next one, y equals 2x cubed minus 4x. The first exponent was 3, which is odd, an odd number. The second exponent, even though we don't have it written, is a 1, which is also odd. So what we could say here is if all exponents are odd, then the function is odd. And to prove that they're neither, you're going to have a mixture. So y equals 2x, let's say, squared plus x. So here, 2 is even, and x to the first power would be an odd exponent. So we have a mix of even and odd. So if exponents are mixed, even, and odd, then the function is neither. Okay? Algebraically prove, graphically prove, check your answers with the exponents. And that's it for the notes.